Let's dive right into this explainer on the engineering of Japan's seismic skyscrapers. When you look up at a massive modern skyline, those towers look completely unmovable, right? Like they're bolted to the earth forever. But today, we're exploring a place where the ground beneath them is actually anything but permanent. We're going to unpack the absolutely incredible engineering that manages to keep these giants standing.
So, why build earthquake-proof skyscrapers in the first place? Well, it definitely isn't just about showing off some fancy architectural prowess. It's an absolute non-negotiable necessity. Japan desperately needs vertical density to house its massive population. But, as we know, building tall there means inviting an immense amount of risk. It's this high-stakes balancing act, trying to reconcile the human need for space with the Earth's absolute demand for respect.
And to really understand this engineering, we have to respect the threat itself, the seismic reality. When we say seismic, we mean anything relating to earthquakes or vibrations of the Earth's crust. But we aren't just talking about a quick little momentary rumble here. Seismic energy transfers in these massive, violent waves. First, you get the fast-moving P waves, and then, boom, they're followed by those incredibly destructive S waves that literally shear the ground from side to side. So when you're engineering a skyscraper, you aren't just fighting gravity pulling down. No, you're battling a dynamic force that's violently whipping the foundation in multiple, totally unpredictable directions.
Which brings us to the skyscraper dilemma: building tall in seismic zones. Just think about the physics for a second. A tall building essentially acts like a giant lever. If you shake the bottom even a little bit, the forces at the very top are amplified dramatically. In fact, in a standard high-rise during a major quake, the top floors can whip back and forth by several meters. It creates this terrifying and, frankly, structurally catastrophic whiplash effect. If a structure is too stiff, well, that amplified energy has nowhere to go, and the building just snaps.
So, when we compare standard construction versus earthquake-proof engineering, we're looking at a complete paradigm shift. Standard construction usually tries to resist force through sheer strength and rigidity, thick walls, super stiff columns. But earthquake-proof engineering, it has to anticipate movement. It has to absorb it, and in a weird way, actually flow with it. It's basically the difference between a rigid oak tree that splinters in a heavy storm and a flexible reed that bends, yields, and ultimately survives.
Getting back to the core engineering of Japan's seismic skyscrapers, we realized pretty quickly that this isn't just standard architecture we're talking about here. It is deep, complex, life-saving mathematics. So let's take a closer look at exactly how they calculate this survival. Engineers essentially juggle three key priorities. First up is countering seismic forces. They do this by integrating massive tuned mass dampers near the roof and base isolation pads down at the foundation, literally designed to just eat up that kinetic energy. This feeds directly into priority number 2, ensuring structural survival. The building doesn't actually have to look pristine after a magnitude 8.0 quake, it just has to stand upright long enough for everyone to evacuate safely. And finally, pioneering earthquake-proof designs. Every single new tower, like the massive Tokyo Skytree for example, acts as a real-world testing ground to push these technologies even further.
But despite all that complex physics, the massive dampers, the flexible materials, everything, and I mean everything, boils down to one primary goal: to build earthquake-proof. This is a strict zero-tolerance baseline. Every single design meeting, blueprint revision, and material stress test is measured against this singular metric. If a flashy design element compromises this primary goal, it's out, completely thrown out, no questions asked. Conquering nature's forces like this requires a really strict, methodical framework. Step 1 is pure acceptance, identifying and quantifying the exact seismic reality of the soil directly beneath your feet. Step 2, that's where the heavy lifting happens, quite literally. You apply the advanced engineering. We're talking about installing those massive deep foundation isolators, huge rubber and steel bearings, to physically disconnect the building from the shaking earth. All of this is done to achieve Step 3, a skyscraper that doesn't just endure an earthquake, but actually successfully rides it out.
So, jumping back to that initial thought of why Japan builds these earthquake-proof skyscrapers, it ultimately comes down to one absolute priority: human life. In a densely packed megacity, a failing skyscraper is an unimaginable catastrophe. This specific brand of engineering fundamentally protects society's ability to wake up and actually function the day after a massive disaster. To wrap up this explainer, I want to leave you with something to think about. As materials get lighter and computer modeling gets smarter every single day, what are the absolute limits of an earthquake-proof skyscraper? Just how far can human ingenuity actually push back against the Earth's most violent events? It's a totally fascinating question, isn't it? And it's one that engineers are actively answering with every single new addition to the skyline.